Hello and welcome to our first lesson of Chapter 2, which is Limits and Rates of Change. So this chapter is going to form the basis of your understanding for the rest of this calculus course. And basically we're looking at what happens when you get really, really close to something, but you don't actually reach it, okay? This will form our basis for finding rates of change. Normally we look at that as slope. And normally in order to find the slope of a line, we need 2 points on that line. And basically what we're going to be learning in this chapter is how to find the slope of a line if you only had 1 point, okay? So for example, if I have f of x equals x minus 1 over x minus 1, we can simplify these and cancel these out and get that f of x equals 1. However, it doesn't just equals 1. This doesn't make total sense because when we first started, we said that x can't equal 1, right? We think about our non-permissible values of this function. We know from way back in Math 11 that even when you simplify a rational, any non-permissible values must still hold. So the function f of x equals 1, if I think of this as y equals 1, this is a horizontal line at y equals 1. So if I actually draw myself a horizontal line at y equals 1, problem with this is that we also know that x cannot equal 1. So what we have here from, again, Math 12, if you covered Chapter 9 and holes and asymptotes and such, we know if there was a common factor that's simplified in a rational, that factor results in a hole. So instead of having just a line at y equals 1, we have a line at y equals 1 with a hole at x equals 1. Okay, we know this to be true. Now what we're talking about is something called a limit. So if I were to write down lim for limit, underneath we usually put x approaches whatever value we want x to approach. In this case, I'm going to have that x is approaching 1 of f of x. This means we're going to take a look at this function, and it's almost like we're walking along the edge of the line and we're getting as close to an x value of 1 as possible. We know we can't ever actually reach that value because of this statement here. We said x can't equal 1. So we never actually get exactly to an x value of 1, but we're going to get very close. So if we walked along the line, approaching this point from the right-hand side, and we walked along the line approaching this point from the left-hand side, we would get very close to a y value of 1 as well. So if we had a point here, the y coordinate would be 1, but we don't have a point here. So we're not saying the limit when x equals 1, we're saying the limit when x approaches 1. We're going to get very close to this point. And as we approach, our y value approaches 1, so this is going to equal 1. Okay? So how we read this is the limit as x approaches 1 of f of x equals 1. Okay. The other way we could write this, because we have an actual function, is the limit as x approaches 1 of x minus 1 over x minus 1 equals 1. The whole idea of limits here is that it's not what does y actually equal at that point, because we don't have a point. Y doesn't equal anything. It does not exist. There is no point. So we're not looking at what does y equal. We're looking at what are we approaching. The whole idea about a limit is what are we approaching. Okay? So our formal definition is the limit as x approaches a of some function f of x is equal to some value L, means the limit of f of x as x approaches a equals L. If we make those f of x values really close to L, x would be really close to a. So L is a y value here. And our picture isn't great, so I'm going to remove this a and stick it here. And I'm going to change this L and add it up here. And hopefully by the time you're doing this lesson, I've fixed your document as well so that it's not so terrible. So f of x will approach L as x approaches A. And remember that f of x is just a y value. So this is like saying y approaches L as x approaches A. Okay. Now we have something called a one-sided and a two-sided limit. So if we say x is approaching 3, that means we're considering both directions. We have to approach from both sides. If we have x approaches 3 with a little tiny plus here, this isn't positive 3. This means we're approaching from the right, meaning we have slightly larger values than 3 that we are considering. If we have x approaches 3 with that little negative, this does not mean negative 3. This means we are approaching from the left, meaning we're considering slightly smaller values than 3. Okay. So for example, this picture here, if this was 3, let's say this is some value 2, what we would say is the limit as x approaches 3 from the right of f of x, we'll call this curve f of x, is equal to 2 because as I travel down this curve from the right-hand side, slightly larger values than 3, like 3.1, 3.01, etc., our y value would get closer and closer to 2. If we took the limit as x approaches 3 from the left of f of x, we would also have 2, because if I were to travel along this curve and I would get very, very close to 3, my y values again would get closer and closer to 2. Okay? What this means is that overall, our limit as x approaches 3 from both sides of f of x is equal to 2. That's what that means. This statement says, this last statement here in the red box says that from both sides, if we approach, we get a value of 2. So something where you wouldn't have the same value would be similar to this example on the next page. Okay. So if I have, again, my x value of 3, let's say this value is 4 and this value is 5, for example. If I take the limit as x approaches 3 from the right of f of x, if I travel along the line approaching that point from the right-hand side, slightly larger values of 3, my y value approaches 5. Okay. If I take the limit as x approaches 3 from the left of f of x, I'm going to be approaching that point from the left-hand side of the function. Okay, slightly smaller values of 3, my y values are going to get closer and closer to 4. Okay. What this means is that the limit as x approaches 4 from both directions does not exist. And this is because they are not the same number. You can only say that you have the limit as x approaches, this should be as x approaches 3 here, if they are the same from the right and the left, because by definition, x approaches 3 is considering both directions. You are not approaching a single number from both directions. You're approaching 5 from the right and 4 from the left. So in the box below here, this is saying the limit as x approaches A is equal to some number L only if the limit from the left is L and the limit from the right is L. So you don't have a limit unless the right hand and left hand limits are the same. Okay. So this would be our final answer for this question. We do not have a limit. We have a right and a left hand, but not an overall limit. And D&E, if you haven't seen this before, it just means does not exist. Okay. So for example, let's take a look at this. We'll do an example here. The first one is saying the limit as x approaches 2 from the left. So x approaches 2 from the left. So if I go down and look at my x value of 2 and I find the part of the function that's to the left of 2, that means we're approaching along this line here. Okay? So we can see that as we travel along this line, we get really close to an x value of 2, our y values are getting very close to a y value of 3. Okay. If we approach from the right instead, this means if we look to the right-hand side of our x value of 2 and look for that part of the function, we're traveling along that side of the function. We're getting very close to an x value of 2. And as we do that, our y values are getting closer and closer to a y value of 1. So you can see that because the two pieces of the function don't have the same y value from the left and the right, our limits are not the same from the left and the right. And what this means is because our left-hand limit is 3 and our right-hand limit is 1, our overall limit does not exist. Okay? So the left-hand limit and right-hand limit are not equal here. Okay? Now let's try again with 5. Okay, so I'm going to erase all my markings here so we've got a nice graph to work with. So if I approach 5 from the left, I'm traveling along this line, approaching that value from the left. My y values are approaching a y value of 2. As I approach from the right, my y values are also approaching 2. So notice g of 5 is equal to, it looks like about 1.5 or 1, right? That's this point here. This is not equal to our limit. Okay. So we're not looking for the actual value of y. We're looking for as x approaches 5, what y values does our function approach as well. Okay. So we actually have a value for y at 5, but that's not what we're concerned about. We're concerned about as x approaches 5, what y values are we approaching, not when x is equal to 5. Okay. So our overall limit here, left and right hand limits are equal. Therefore, our overall limit is 2. We also have what happens if we have like an asymptote, right? So we've seen now here what happens when the function jumps from one value to another, which we saw as x approached 2 in this example. We saw what happens if you have a hole and then a point somewhere else. That's what happens when x approaches 5. If there's no funky stuff going on here, it's just going to approach whatever y value we actually do equal. But our other situation is asymptote. So there's a couple different things that you might see. Okay. So one of the things you might see is what we're used to seeing when we have a rational where you have like these two kind of L-shaped bits. Okay. And let's call this some value A. Okay. So we would have the limit as x approaches a from the right of our function would be negative infinity, because as we approach from the right towards a, we can see that our y values are all decreasing, going down forever here. Okay. If we had the limit as x approaches a from the left, this would equal positive infinity, because as you approach that a value from the left, this y value is increasing forever. So therefore, our overall limit would be does not exist, because one of them is infinity and one of them is negative infinity. Okay. Now, the other situation you might see, some problems with our touch screen here, is the two L-shaped things could go in the same direction. Okay, so again, I'm going to say this is some x value a. So here, if I have the limit as x approaches a from the right of f of x, this would be infinity. The limit as x approaches a from the left of f of x would also be infinity, and therefore our limit as x approaches a of f of x would be infinity. So it's important to note that infinity, we will never reach that. Infinity, we can't actually get there. So technically, this also does not exist. We are just being more specific as to why it does not exist. Okay. If I have something like this, where the limit does not exist at all, and it actually states DNE does not exist, this is telling us our left hand and right hand limits were not equal. Okay. The second version here, where we equal infinity, again, technically we can't get to infinity ever, but we're being more specific as to why we don't exist. So our limit doesn't, you can't equal infinity. We don't actually get there. So our limit does not exist, but we state it equals infinity simply to tell the reader we are approaching infinity from both the left and the right. Okay. So when you guys get to university, depending on your professor, they might hate that you've written equals infinity because you can't, right? Um, so again, proceed with caution when you get to university as to what they tell you to write down. In the textbook, they will write equals infinity here, okay? Now, what this tells us is if any of our limits equal infinity, even if it's just a left hand or a right hand limit, like these ones, or if we equal infinity overall, this tells us both of these things, that we have an asymptote at x equals a. And if we think about this logically, this makes sense, okay? If we approach an x value and our y value goes towards infinity or negative infinity, it makes sense that we would have an asymptote there. Okay? So on the next page, it was just another opportunity to show another example of what this might look like. We might be maybe approaching negative infinity instead. Okay, you could be going down like this instead. Okay, and this would be the limit as x approaches a of f of x equals negative infinity. Okay, so in the box, it just says that you have a vertical asymptote at x equals a if you are approaching positive or negative infinity from either the left or the right. Okay, so you don't have to be approaching from both directions. And there's an example below of what that might look like. Something like this, okay, which looks kind of like a logarithmic graph. You can see there is no part of the function on the other side of our asymptote. Okay, so the limit as x approaches 2 from the left does not exist because there is no function on the left. There's nothing there. Okay. And the limit as x approaches 2 from the right would be negative infinity. So they do not both have to approach the same thing. This one approaches negative infinity, and so therefore we have a vertical asymptote at x equals 2. So it does not have to be overall, left or right. Now, a lot of these questions, like number 3, you're going to take a look at and you're going to go, well, I already know where that is. I did math 12. I know my vertical asymptote is at x equals 3. We have a non-permissible value of 3 on the denominator here. But the whole point is that you're using calculus to find this. So if you had a question like this in university and you just said, well, x can't equal 3, and therefore we have a vertical asymptote at 3, that's not what they're looking for. They want to understand that you know to consider the left and the right hand limit and how that works. Okay? Because we don't have a graph here, basically what we're going to do is when we look at the left and the right hand limit, we're actually going to consider values that are slightly bigger and slightly smaller than 3. Okay? So if we have the limit as x approaches 3 from the right of 2x over x minus 3, if we plug in a value slightly bigger than 3 on the top, what's going to happen is the top is going to get really, really close to 6. but it's going to be slightly larger. Okay. On the bottom, what's going to happen is if you plug in something like 3.1 or 3.2 or 3.01, that bottom, the closer you get to 3, that bottom number is going to get really close to 0. So for example, if x equals 3.1, you're going to have 2 times 3.1 over 3.1 minus 3, which will give us 6.2 over 0.1. If x is equal to 3.01, you have 2 times 3.01 over 3.01 minus 3, which gives us 6.02 over 0.01. You can see that the top, as you get closer and closer to 3 from the right, the top number is going to get very close to x, but be ever so slightly larger, and the bottom is going to approach 0. And what that means is you're taking 6 and you're dividing it by a smaller and smaller number. So if you think about it, what happens when you take 6 and you divide it by a really, really, really small positive number? And that number gets smaller and smaller. Well, if you actually try that on your calculator, you'll see your answers are going to get bigger and bigger. So if I take 6 and I divide it by 0.1 and 0.01, 0.001, and smaller, this is going to get bigger as you approach 3, which means this would approach infinity. Okay. If I think about this logically, this makes sense. I basically have 6 on the top and I have a teeny tiny number on the bottom. If I divide, I'm going to get a really big answer. The smaller I make the number on the bottom, the bigger my answer is going to be. So eventually that answer is going to become absolutely huge and approach infinity. Okay. We can try this from the left as well. So again, if I plug in a slightly smaller number on the top, something like 2.9, the top is going to approach 6, but it's going to be slightly smaller. Okay. The bottom is going to still approach 0, but it's going to be negative. So we'll just say that this is from the right. So for example, if x is equal to 2.9, we would have 2 times 2.9 over 2.9 minus 3. So you're going to get 5.8 over negative 0.1. So the difference here is, again, the top is going to get really close to 6. The bottom is going to be a teeny tiny number, but negative. Okay. So as soon as I have that teeny tiny negative number, that means that this is actually going to approach negative infinity instead of positive infinity. Okay. So our overall limit would not exist. We weren't asked for that. But our limit from the right is infinity, and our limit from the left is negative infinity. Therefore, we have a vertical asymptote at x equals 3. And we wouldn't have needed both of these. One of these would have told us we had a vertical asymptote at 3. As x approaches 3, y approaches plus or minus infinity. So you'll see on the bottom a ton of practice questions. In the photocopy of the 5th edition, there's just a couple questions there. Any even numbers never have answers in the back of the textbook, so the even answers are written on the bottom here for you. And then in the 7th edition, there's also some questions, odd numbers, except for number 8. Um, there are usually way more questions than you will need. Do what you need to do. There's a couple of the photocopied questions where the graphs maybe aren't so clear. So some people, for example, there's one where people say, well, it looks like the limit is 4, but the answer in the back is does not exist. So there's a couple where you might be kind of going, well, we're all getting the same answer here and we don't understand why. If you have a question like that, please ask, but also consider the fact that the photocopied version might just not be as clear. And so they might have a different answer because of that, because there might be a point you can't see that was in the original. So if you're having one where you're working with some friends and you're all getting the same answer, and it's not the answer in the back, If you think you're doing something wrong, please ask, but also take a look at the picture and kind of consider if you can actually see it properly or not. Okay.